In this section, we will investigate the trigonometric or polar form of complex numbers. In doing so, we will look at the complex number plane and vector representation, the trigonometric or polar form, and the product and quotients of complex numbers in trigonometric form. Hello, my name is Tom Atwater. We're going to begin today by looking at how to express complex numbers as a vector. We have the vector, or the complex number, to start, 2 minus 3i. It is made up of a real part and an imaginary part. And you can see that the x-axis represents the real axis or the horizontal component. The y-axis represents the imaginary axis or the vertical component. So the way that we draw the vector is by doing the horizontal component, which is the real part, horizontally, and then drawing the imaginary part vertically, and then connecting the origin to that point, P. And that vector then is representative of 2 minus 3i. Well, what I'd like to do is an example where we are asked to express the sum of complex numbers graphically. Find the sum of 6 minus 2i and negative 4 minus 3i. Graph both complex numbers and their resultant. So what I'd like to do for you first is to find the sum algebraically. So we're going to take the two complex numbers and add them together. So we have 6 minus 2i, to which I will add negative 4 minus 3i. And the way we do this is you take the real parts and add those together first. So 6 plus negative 4 gives me 2. Then you combine the imaginary parts. Negative 2 plus negative 2i plus negative 3i gives me a total of negative 5i. And I can express it as 2 minus 5i. Well, now let's take a look at graphing the two complex numbers as vectors and see what their resultant is. So we have 6 minus 2i, which is the complex number represented by the vector ending here. And we have the complex number negative 4 minus 3i, which is the vector from the origin to this point. Of course, we know that we draw our parallelogram, and the diagonal of the parallelogram would be the resultant of adding together those two vectors. And we'll see that it in fact gives us the answer that we calculated algebraically, which is 2 minus 5i. So the graphic showed the complex number x plus yi that corresponds to the vector. And let's take a look now at that same type of situation of the vector, but in what we call standard position. All right, so here we have the complex number x plus yi, and that corresponds to the vector OP, which has a direction angle of theta and a magnitude of r. Let's look at what the relationship is between x, y, r, and theta. We have that x is equal to r times cosine theta, and y is equal to r times sine theta, where r is equal to the square root of x squared plus y squared, and tangent theta is equal to y over x. And again, where x cannot be equal to 0. These relationships lead us to the trigonometric or polar form of complex numbers. So let's take a look. The expression r parentheses cosine theta plus I sine theta is called the trigonometric form or polar form of the complex number x plus yi. The expression cosine theta plus I sine theta is sometimes abbreviated as CIS theta, which is sometimes said as cis theta, but some books call it kiss theta. Either one is acceptable. Now, using this notation, r times parentheses cosine theta plus I sine theta is written as r cis theta. Let's now look at an example where we are asked to use this trigonometric form. Express 2 times cosine 300 degrees plus I times sine 300 degrees in rectangular form. So what we want to do is convert it from one form to the other form. So what we know is that we have r, in this case is 2, times the cosine of 300 degrees plus I times the sine of 300 degrees. Well, in the case of cosine of 300 degrees, you would recognize that as a special angle because its reference angle is 60 degrees, and it is in quadrant number 4, where we know that cosine will be positive, sine will be negative. But the special angle is 60 degrees. The cosine of 60 degrees, remember, is 1/2. The sine of 60 degrees is the square root of 3 over 2, but when we get to the sine, remember, it is negative. So what we have then is 2 times 1/2 minus, because it's negative, I times the square root of 3 over 2. When I distribute the 2, I end up with the answer 1 minus I square root of 3. And that would then be the rectangular form. Now notice that the real part is positive and the imaginary part turned out to be negative, which is what we would expect because it puts that vector, if we were to draw it, into quadrant 4. This, of course, is consistent with 300 degrees being in quadrant 4. Before we try a problem converting from rectangular to trigonometric form, let's look at the steps for this conversion process. Step 1, sketch a graph of the number x plus iy in the complex plane. Step 2, find r using the equation r equals the square root of x squared plus y squared. And step 3, find theta by using the equation tan theta equals y over x, where x is not equal to 0, choosing the quadrant indicated in step 1. Well, let's do an example where we apply those 3 steps. So, write negative square root of 3 plus I, using radian measure, in trigonometric form. So, we would start by sketching that, and you can see that we have the vector negative 3 plus I, which lands us in, of course, the second quadrant, and connecting the origin to that specific point. We know that x is equal to negative square root of 3. We know that y is equal to 1 because the coefficient on I is an understood 1. When we do the calculation for r, which of course we know is equal to the square root of x squared, which is the square root, negative the square root of 3 squared plus 1 squared. Then we get 3 plus 1, which is the square root of 4, and the square root of 4 is 2. In terms of the angle theta, we find that that's 5 pi over 6 because when we look at the tangent of theta prime, the reference angle theta prime, the tangent would be the opposite over the adjacent, so 1 over negative square root of 3, which gives us an angle for theta prime of pi over 6. But of course, that's the reference angle theta prime. Realizing that it's in the second quadrant, we subtract pi over 6 from pi, pi being this angle here, and we get our angle of 5 pi over 6. So negative the square root of 3i, negative the square root of 3 plus I converted to polar form would be 2 times the cosine 5 pi over 6 plus I sine 5 pi over 6. And in the abbreviated form, it would be 2 cis 5 pi over 6. All right, so now I'd like you to try a problem. Write 3 minus 3i in the trigonometric form r parentheses cosine theta plus I sine theta, where r is exact and theta is between negative 180 degrees and positive 180 degrees. Now pause the video while you work on this problem, and when you are finished, restart the video to check your solution. So let's find out how you did on that problem. We have the problem 3 minus 3i, and you want to find the polar form, which means calculate r. R is equal to the square root of a squared plus, x squared plus y squared, which would be negative 3 squared. So we have 9 plus 9, which is the square root of 18, which when we simplify it, and remember we were asked to keep it exact, that would be 3 square roots of 2. Now we need to find theta. So we do tan theta, and that will be equal to the y value over the x value, or negative 1. That, of course, is one of our special angles of 45 degrees, or pi over 4 if we do it in radians. And tangent of theta, the restrictions we were given were from negative 180 to positive 180. And so in this case, we're going to have the tangent of theta being in quadrant 4. That's where tan is negative. So we would use negative 45 degrees, or again, negative pi over 4 would be acceptable. So now we combine this into 3 minus 3i is going to be equal to r, 3 square roots of 2, times cosine of negative 45 degrees plus I times sine negative 45 degrees. And in the abbreviated form, it would be 3 square roots of 2 cis negative 45. All right, great job on that. Now, in order to multiply complex numbers in rectangular form, we can use the FOIL method that we know about. If the numbers are in trigonometric form, we can use what's called the product theorem, which I'll show you now. If R1 times cosine theta 1 plus I sine theta 1 and R2 times cosine theta 2 plus I sine theta 2 are any two complex numbers, then if we multiply those two together, that will equal R1 times R2 times brackets cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. In compact form, this is written as R1 cis theta 1 times R2 cis theta 2, and that's going to equal R1 times R2 times cis of theta 1 plus theta 2. Well, let's look at an example that illustrates this theorem. So find the product in rectangular form using exact values. And we have 3 cosine 60 plus I sine 60 times 2 cosine 90 degrees plus I sine of 90 degrees. So using that theorem, we start off by multiplying the two r's together. And the two r's are 3 times 2. Then we add the two angles together, and the two angles are 60 and 90. So it would be the cosine of 60 plus 90, or in other words, 150 degrees, plus I times the sine of adding the two angles together, 150 degrees. So now we take, this of course is 6, so let's write that. And then we want the cosine of 150. 150 degrees is quadrant 2. And in quadrant 2, cosine is negative. The reference angle is 30 degrees. So we want the cosine of 30 degrees, and we'll make it negative. The cosine of 30 degrees is the square root of 3 over 2. Now we take plus I times the sine of 150. 150 is in quadrant 2, sine is positive. The sine of the reference angle 30 is 1/2, so it's positive 1/2 for there. Now we distribute a 6, and 6 times negative radical 3 over 2 gives me negative 3 square roots of 3. And then 6 times 1/2 I gives me plus 3I. So that gives me the rectangular form of the polar form. All right, now let's take a look at the quotient theorem, where we can divide complex numbers. If r sub 1 cosine theta 1 plus I sine theta 1 and r sub 2 cosine theta 2 plus I sine theta 2 are complex numbers where r sub 2 cosine theta 2 plus I sine theta 2 is not equal to 0, then if we divide those two complex numbers, our solution is R1 divided by R2 times the quantity cosine of the difference of the two angles plus I sine the difference of the two angles. And in compact form, we would write it this way. R1 cis theta 1 divided by R2 cis theta 2 would be equal to R1 divided by R2 times cis theta 1 minus theta 2. Well, let's take a look at an example where we divide complex numbers in trigonometric form. Find the quotient in rectangular form, 10 cis of negative 60 degrees divided by 5 cis of 150 degrees. So to do this problem, I'm going to use abbreviated form. We start off by dividing the two R values, 10 divided by 5. And then we use cis of the difference between the two angles. Now, the first angle was negative 60. And from that, I would subtract 150. So that what I get is 10 divided by 5 is 2, cis of negative 210 degrees. Now, negative 210 degrees means we start at the positive side of the x-axis and go in this direction, and I'll go past 180 degrees, so I land in quadrant number 2. Therefore, the angle that's my reference angle is 30 degrees. Cosine will be negative, sine will be positive. The cosine of 30 degrees is equal to square root of 3 over 2. The sine of 30 degrees is 1/2. But remember, cosine will be negative. So what we have is 2 times negative square root of 3 over 2 plus I times positive 1/2. Distribute, and I end up with negative square root of 3 plus I. And that would be my rectangular form of the original quotient. Great job using polar form of complex numbers. Now, in this lesson, we investigated what's called trigonometric or polar form of complex numbers. And in doing so, we looked at the complex number plane and the vector representation of that, as well as the trigonometric or polar form and products and quotients of complex numbers. Be sure to work the exercises that your teacher assigns, and we'll see you next time.